Hello and welcome back to Calculus 1, section 2.5, limits at infinity. So how's this different than the previous section? It was infinite limits, and now limits at infinity. So now we are looking at limits where x goes to positive or negative infinity, and we will have either finite value or one of the infinities back. So this is the type of the limit that we are considering now. So let's take a look at an example. How much is the limit as x goes to positive infinity of x plus 5? And the answer is infinity. Because in air quotes, when you plug in infinity, infinity plus 5 is infinity. So we can also take a look at the limit as x goes to infinity for 1 over x. And we get what? What do we get? Yes? 0. If you are to graph 1 over x, and you see how x goes to infinity, you see that the y value is trying to hit the 0. So imagine the point here, right? And then it's closer, and it's closer, and it's closer, and you see that the y value is trying to hit the x-axis. X-axis has y equals 0, which is, we know that the limits are the y value for the function. So now you say, all right, so what if I have limit x goes to infinity for 5 over x? And the answer is still 0. Because of those rules that we learned last class, where we can take this 5 and write it as 5 times 1 over x, and we can kick 5 in front of the limit and have 5 times 0 equals 0. So it's still 0. Now the question is, what is this good for? These particular problems that I have, they're good so that we can see that if we divide something by infinity, we eventually get 0. So if this is 1 unit, when I divide this by 2, it's equivalent of ripping it in half. So now I have half. If I divide half in a half, that's like dividing the original value by 4, right? Because I divided by half and by half again. If I divide this in half, then it becomes 1 over 8. So you see how the denominator rises from being 1 for the whole unit, and then when I divided by 2, it became a half, and then a quarter, and then an 8. Now it's already up to 16, and then 32, 64, 128. This means that there were 128 of these pieces in the original piece of paper. 256, right? And it's getting harder for you to see it from the back row because, right, here's the 512. So 512 of these guys were in the original paper I had. Now, you can see that as denominator grows to infinity, what's happening with the size of the paper? Right? Gone. Magic, right? So it doesn't matter if I rip 5 papers apart or I rip 1 paper apart. If I divide that infinitely many times, which is that x in denominator goes to infinity, which means I'm chopping it infinitely many times, the actual paper goes to nothing, goes to 0. It's a very important concept for you to remember. So I might write it as a formula, but just know the concept. So limit 1 over x to the any power p, right, as long as p is larger than 0, is going to be 0 if x goes to any of the infinities, positive or negative. We're going to actually use this in problems in this section. So we want to know this. Cool. So what's the next step? The next step is to solve a slightly more complicated problem, which says limit x goes to infinity for, let's say, x squared plus 3x minus 1 divided by x cubed plus 8, whatever. Now we want to do this problem. What is the procedure? The procedure is to realize that there is the highest exponent somewhere, in this case cube, and we are going to divide each one of these terms by x cubed. So I still have my x squared plus 3x minus 1 divided by x cubed plus 8, but I'm going to divide each one by x cubed. And then we're going to cancel. So what I get is 1 over x minus 3 over x squared minus 1 over x cubed divided by 1 plus 8 over x. And we know, because of the rules, again, from last class, that when you apply the limit, you apply to each term individually. And we have the red formula up there. So that goes to 0, that goes to 0, that goes to 0, that goes to 0. All of the terms except that 1 go to 0. We get 0 divided by 1, which is 0. So the limit for that problem was 0.
Hey, Professor?
Yes.
It's supposed to be plus 3 over x squared. Is that minus? I know.
Plus, yes. Yes, it is plus. Good. Well, it didn't matter in this problem. In some other problem, it might matter. So, good catch. I was just testing you, and you just passed. Don't laugh. Everyone else failed. You see something, you have to say something. Right? Oh, you guys don't go to airports? Oh. What?
Don't be a zebra. Never heard that?
No.
They stand there and watch while the other zebra get eaten by lions. And they just sit
Yeah,
there.
but what are they gonna do? I mean, like, put yourself in a zebra skin, and then there is a lion eating another zebra. What do you do?
I'd be out of there pretty quick.
Yeah, but this is the only source of water for, like, you know, for like the whole continent. Okay. So what are you gonna do? So no, I haven't heard that, but I'll have something to think about on my way home.
It's like that high school thing. They claim not to be a zebra,
Yeah.
so like people don't get bullied. You're supposed to like stand up
So you have to go and actually bully the person that bullies the other person, or no? Yeah, I don't understand those. I came from a different culture where if you bully someone, someone bigger is going to come along and just punch you in the face. That's how it goes, because it's a friend with the person you bully. So I don't understand how those things work here. I wasn't in a high school, so.
Where are you from?
I'm from Serbia. It's a very long swim.
You should see high schools now. They got safe spaces.
What is that?
It's a room with beanbags
With
that you go if your feelings are hurt.
With the padding, or no?
I don't know. Hillsborough, they have that. It was like 2 years after I left.
So you just go there and you punch things?
I don't know. It's like
I don't think it's supposed to be physically safe.
yeah, no, not physically safe. It's more like you can essentially just raise your hand and be like, my feelings are hurt or I'm uncomfortable, and like they have to let you go there. And they wonder why there's a generation full of sissies.
We should make a safe room. Please. Would anyone escort Dalton to, yeah. Except the only room we have available is the generator room in the back. Just don't touch any of the moving parts. Yeah. All right. Or touch. I mean, nothing I can do. That's another part of how I was raised. Touch this, it's hot. Ow! See, you will never touch it again. Or by example. All right. 1 second. Infomercial. Okay, let's do more calculus. This is awesome. We're all learning today. I learned something new.
Don't be a zebra.
Yeah, zebras and safe rooms so far. All right, great. Keep bringing the concepts. What else are we supposed to do? Some more math. So, what would be the major concept, mathematical concept that we are going to use this for? Horizontal asymptotes. Very good. And then there's one more thing. Abbreviate as HA. So the theorem, definition, whatever, goes that if the limit as x goes to positive or negative infinity of f of x is equal to some finite number L, then we have horizontal asymptote at y equals L. So that would be something for us to consider. So now I'm going to immediately go with the easiest possible case. X goes to infinity for 1 over x. We said already it's a 0, which implies horizontal asymptote at y equals 0, which is x-axis. Now if you draw this function, which we drew like 15,000 times already, we can see using our eyes that there is a horizontal asymptote at y equals 0, which is the x-axis. Now, for this particular problem, it didn't really matter whether we are going to use positive or negative infinity as, for the limit to go to. Positive or negative infinity, doesn't matter. But for some problems will matter. Say e to the x. So limit x goes to, and I'll just say e to the x dx. So do you want to go to positive or negative infinity if you want to check whether e to the x has the asymptote or no? You want to go to negative infinity. Very good. Why do I put dx there? I just went like 3 chapters. E to the x. And what's the answer? 0. Very good. 0. The answer is 0. So here's my favorite. Limit of inverse tangent of x as x goes to infinity. I heard something really cool. Pi over 2, would you bet your money on it? Would anyone bet money on his pi over 2? You want to bet against it? That's some confidence right there. So yes, very good. Pi over 2 it is. Oh, now you sound like my 4-year-old. All right. So can I just say now because and be done? Awesome. Gotta know the graphs. So if the tangent graph looks like this, and the domain goes from negative pi over 2 to positive pi over 2, then the inverse graph must look like the one that I have on the right, with the range being pi's over 2, because that's how it goes. Awesome. Didn't you memorize some kind of rules for this in pre-calc 1? For rational functions, when you divide 2 polynomials, some kind of rules for horizontal asymptotes? Should I upgrade or downgrade some grades? I should. Anyone remembers the rules? There were 3 rules regarding the exponents.
Like N and M?
Mm-hmm. Yeah, so you are kind of, so you can forget it now. Good thing is that you don't need it anymore. So if you don't remember it, don't worry about it. That's technically what I wanted to say. The rule goes: the higher exponent in the numerator, no horizontal asymptote. If the exponents are the same, it's the front coefficients and the ratio of front coefficients. And then if the higher exponent is in the denominator, then horizontal asymptote is at 0. But you don't need to know that anymore, because now you have the limit to prove that every time. So say you have limit as x goes to infinity for 3 plus x squared divided by 2x squared minus 1. What's the horizontal asymptote? 1/2. Just by looking at it, it's 1/2. If you know if you memorize the pre-calc rules, same exponents, so it's just ratio of front coefficients, which is 1 divided by 2 is 1/2. But then, this being calculus, we are going to do the awesome thing. Because eventually someone is going to ask why, and I have to cover that. So what do we know? This is going to go to 0 because limit of 3 over, right? This guy over here. 1 over x squared, 1 over x cubed, 1 over, or whatever number over x to the any power is always 0. So going back to our problem, that guy goes to 0. This guy goes to 0 as well by the same rule. That's your 1, and that's your 2. So boom, 1/2. I believe they have some very interesting problems for these ones. Ah, they do. This is awesome. Four x cubed plus 1 divided by 2x cubed plus square root of 16x to the 6 plus 1. And the answer is clearly 2/3, but how to get that? You know that you're looking at. What's the procedure to solve these problems? We just did it. Can't because of plus 1. Can't take anything out of square root. What is the procedure?
Well, you rewrite it as like 2x cubed plus square root of 16x to the 6 plus the square root of 1.
Why?
Because then you can take it out.
It's not going to help. Divide every single term, and you have 4 terms there, by x cubed. And then on that square root, the x cubed will go inside the square root and stuff will happen. All right, let's see how your algebra goes. Very good, very good. So divide each term by x cubed. Over what? It's not gonna help. You just have to undergo, because it will be square root divided by x cubed. You have to bring that x cubed under the square root. And it becomes what? When x cubed goes under the square root, it becomes what? Nope. Nope. When x cubed goes under the square root, it's kind of backward thinking. X to the 6, good. So when you put that x cubed under the square root, it has to be x to the 6, which is actually what you needed, right? It was awesome. Kind of worked out nicely. So we know that these guys will go to 0. And what you have is limit x goes to infinity. Oh no, no more limit because we just did that. It's 4 over 2 plus square root of 16, which is didn't I promise 2/3? It's just because I'm lucky, I guess. No, better, psychic. Yes.
Why that become x to the 10th?
To the 10th?
16 x to the 10th.
Over here?
Yeah.
That's a 6.
Oh, okay. Go.
All right. Great. That's that. Now, one more concept. We can use this for horizontal asymptotes, but we can also use it for end behavior. Oh, actually, wait, there's a slant asymptote as well. First off, slant asymptote happens only in one case. It's not a major stuff, but let's talk about slant asymptote for 17 seconds. So slant asymptote and horizontal asymptote cannot occur at the same time. Slant asymptote shows up only when we have x to the p divided by x to the q, where p is q plus 1, which means the exponent in the numerator is by 1 higher than the exponent in the denominator. It only works for polynomials. And if you think about it a little bit, clearly upon the long division, when you divide, you will get a linear equation. So if you have a function f of x equals to, let's say, x cubed minus x plus 1 divided by, I don't know, 2x squared plus 3, slant asymptote? The answer is yes, because the power and the exponent is by 1 larger than the power in the denominator. And now we also know that there is no horizontal asymptote there, because the higher exponent on the in the numerator. And where is it? The answer to that is long division. If you remember long division of polynomials, you will be able to find where this value is. So 2x cubed plus 3 divided into x cubed minus x plus 1. It goes 1/2 times. Sorry, this is supposed to be a square over here. So it goes 1/2 x times, and if you multiply it back, you will get x cubed plus 3/2 x. And now when you subtract these, you get 0, and then you get plus 1/2 x plus 1. Now 2x squared does not go into 1/2 x because that's x squared and that's x, so that's it. Y equal 1/2 x in this particular, right? Plus 0 on the b. So you will use long division of polynomials. There's about 60,000-70,000 YouTube videos on how to do long division if you forgot. But that's for the slant asymptote. And there was a little side note. The large part that we need to know is the end behavior of functions. And that is another big aspect of horizontal asymptotes. So what we have here is, I will talk about f of x equals e to the x. We know the graph. Better know the graph for e to the x. Now observe that we can go to negative infinity and we can go to positive infinity. If I write limit x goes to negative infinity for e to the x, we already know we're getting 0. And that is the horizontal asymptote at y equals 0. But you can also say limit x goes to positive infinity of e to the x and get infinity. Now that is the end behavior, where you know that as you go to infinity in positive x direction, you will go to infinity as the answer for the function. Now, this part is very easy to understand using the visual cues, because you can have function to go like this, like that, and like that. So this one is the limit x goes to negative infinity of f of x, giving you positive infinity as the answer. And the one below is limit of f of x that gives you negative infinity as the answer. Over here we have limit x goes to positive infinity and gives us the positive infinity back. And over here we have limit f of x that gives us negative infinity as x goes to positive infinity. So that's all you can get. Remember, you can draw a quadratic function. Then that's the top two. You can have a cubic function. Well, then that's the diagonal ones, right? You can, that also works for tangent. You can have e to the x. E to the x is a combination of the vertical asymptote, horizontal asymptote on one side, and then end behavior right here on the other side. So end behavior is there. It was there in your pre-calculus course, and now we just understand the end behavior of the function through the limit. Because you want to see later on in mathematics, when you work on mathematical models, you want to see what happens with your mathematical model using limits, especially in differential equations. So you all learned the population formula in your pre-calculus class. The question is if you remember it, that's a different story. But you all learned the exponential formula for population. Now, this is good on the short run to check, how things work on a small time scale, 10 years back and forth. But this formula is garbage if you have to take a look over a large period of time and then poking into infinity. Because if this formula is going to predict the population of humans on Earth, well, the limit of p0 e to the kt as t goes to infinity is, right? And now this is how we know that this model is not good, because we know that the planet cannot sustain infinitely many people on it, right? There is the carrying capacity of the planet. So I will touch upon that eventually. So we know that this model is bad for long-term calculations. So we have to use it locally. So end behavior of functions tells us that. And then also you take these limits and so on to figure out, charge for the battery so they don't explode. That's another thing. There's a lot of application for all of these things, but so end behavior is if your input is infinity, output is one of the infinities, and you get the horizontal asymptote when the input is one of the infinities, and you get the finite number, positive, negative, 0, whatever you get, that's where the horizontal asymptote is. Y equals that number. I'm out of text again. That's it. Let's do one more example from homework or exercises.
It's like I would know like how to move the equation around.
Don't worry about it. You didn't even set it up yet. You know that the definition. Start with the definition.
Of the horizontal asymptote.
Yeah. You plug that in, and then you see what you can do. You have to write it out first. Right. Limits. And then you see which infinity does what. One
Just
will.
confusing.
What do we have?
Just
Got it.
Horizontal asymptote is one part, and then the other part will give us end behavior. All right, so let's take a look. This is exponential function. So you can also write it, if it's going to make you happier, this way. And you should recognize it immediately as, from your Pre-Calc1 course, as a decay function, which you can sketch real quick. So just by looking at the graph, limit as x goes to negative infinity of our problem is immediately giving you positive infinity. So that's end behavior, because as you go to negative infinity in x, you go to positive infinity on y, because the function goes that way. And as the limit x goes to infinity of 50 over e to the 2x, you get 0, because as you go to positive infinity on x, this y values are constantly approaching the x-axis, going towards 0 without actually being 0. So that part is the horizontal asymptote, and we know horizontal asymptote at y equal to 0. So we have the end behavior, which is this part, and we have the horizontal asymptote at 0. Cool? Of course, cool with math, right? And now they have these problems that unite problem. So find, this will be the last problem for today, and then we're going to go do the lab and divide people and so on. So find all asymptotes. How many different types of asymptotes do we have? How many? 3. Horizontal, vertical, and slant. Good. So find all asymptotes. It really makes me sad and depressed on the exam when I say find all asymptotes and I put the function, and then everyone but 2 students figures out all horizontal and vertical, and only 2 students mention slant. Don't discriminate. That's not nice, right? They should have room for that too. Same room. So find all asymptotes 4, and here's your function to enjoy. This is problem 57 in the textbook. X squared minus 9 divided by x times x minus 3. So this is problem 57 in the textbook section 2.5. All right, go. You can talk to people next to you. Eventually, I'm going to go around and ask you to tell me other people's names. All right? So.
Oh. So no matter where it is. Yeah, exactly.
Top three is lined up for us outside. It's an hour until the class begins.
I'm just super excited for that.
No, they get it. Calculus1 still doesn't get it. There's some time. All right, so do we all see an asymptote at 0, vertical? So we start with x minus 3 equals to 0, x equals 0, x equals 3. So those are our candidates for vertical asymptote. Now, we know that x minus 3 will cancel. So if I go here and say x minus 3, x plus 3 over x minus 3, these guys cancel. All I'm left with is x plus 3 over x, which immediately means that 0 is the vertical asymptote and x equals 3 is the open circle. Now we do have proof for that. If the problem says prove, then you will crank the limit. We also have, so we found vertical asymptote already. And we also have the horizontal asymptote now, where the limit x goes to infinity of x plus 3 over x, which we solve by quickly dividing everywhere by x. I mean, if you know the rule, it's front coefficients, right? And then this one goes 0, so we get 1. Since we got the value, we know that horizontal asymptote at y equals 1. Since we have horizontal asymptote, we cannot have slant asymptote because they're mutually exclusive. So writing no slant asymptote is 2 points. If you actually had to compute it, probably would be 4 points. So don't miss on those points. If it says all asymptotes, as I said, do not discriminate, all right? Look up into slant asymptote as well. Yes? Understood. Questions, concerns?
How do you know that x equals 3 is the open circle again?
Because that's the one that canceled here.
Okay, yeah.
So in the limit will not give you infinity because it's not there. Anything else? Because you have horizontal. You can't have both at the same time. All good? All right, that's it for the class time by stream.